Okay, so um, today I thought I would go through this. So um, this is a lean package, beginner's guide to tactic programming. I've done some tactic programming in lean before, but I feel like it always sort of slips off of my brain cells. So um, so I thought I would do this. Right, let me see. So this is the actual introduction to tactic writing in lean. It's basically a single lean file, so I've already copied it out here. I basically just copied it um, into like the online lean sandbox or whatever. And so if you're interested in lean tactic writing, we assume you already know lean and probably use VS Code, so you can clone it or you can just paste it right in. And so that's what I've done. So I thought I would just go through this and sort of, try and see how well I can understand the concepts. So this tutorial is intended for people with basic knowledge of lean and some basic programming experience will be interested to know how to implement a custom tactic. Ideally, open this file in VS Code to see how lean reacts. Yeah, and so in fact, what I have done is I've opened it in liveleanlean.org. After going through the tutorial, a decent overview of what metaprogramming is about and some simple tactics, ability to write simple tactics. Great. So tactics in general are arbitrary programs that operate on the proof state. You can write such programs in place in the tactic proof, such as in the following example. This example tactic doesn't do anything except logging hello world. Put your cursor at the blue underlined run tac to see the message. Okay, run tac. It says, in fact, hello world. Wonderful. And in fact, what it has done to produce this hello world is that it has done this lean.loginfo, which I guess, there's a million different like monad related type classes in this argument, but it's just something that presumably logs an information message using the given data. Okay, that's fine. Sorry, what exactly is the lean.message data? So I guess the hello world string is a lean.message data rather than a string. That's interesting. Okay, well, technically as a string, maybe it gets cast to a lean.message data. Not sure. Do not bother with the type. Okay, yes. Do not bother with the type so too much. It is simply a logging printing function. Cool. To understand how to write tactics, we need to understand 1, how imperative programs work, 2, what really is a proof state, 3, what are some basic data structures around metaprogramming, 4, some API, and 5, how to declare syntax for a new tactic. Okay, cool. Let's answer. 1, how imperative programs work in lean. Lean is a pure functional language compared to imperative languages like C and Python. Its definitions cannot change, and its functions depend only on their arguments, and it cannot have side effects. However, functional programming languages such as Haskell developed a way to write imperative style through monads and do notation, which hide the monads from the user. We will keep the monad theory hidden. Here we just say that a monad in general denotes an imperative program. There are several monads depending on what state they have access to. In the following example, we show 2 monads. First monad is lean.alab.tactic.tacticm, the top level tactic monad, which has access to all the data from the proof state. Okay, cool. So I think basically what I'm getting from this is that when I write a tactic mode proof, like the by perhaps is is really just a do in disguise maybe, and I'm just running a bunch of tactics. Although I don't know if that's entirely accurate, but that's the sort of way I think of it sometimes. The other monad is the meta-m monad. Only has access to information about meta variables. Not important for now. Okay, a part of the entire proof state. So tactic m can call a meta-m, but not the other way around. Okay, cool. We will now demonstrate imperative programming in lean with some examples. So far, we are not using any API to access the proof state, only showcasing lean as an imperative programming languages. Okay, yeah, sure. So meta-m nat, so it returns a nat, right? We have a monadic function that returns a nat. If n equals 0, since we're in do notation, we can skip else. Yeah, so this is like do unchained or whatever. So if n equals 0, we return 42. Otherwise, let k equals n squared. We log some info. And I guess this is like a format string, so I guess we log the input and the output, and we return the output. Cool. So that's my code 1. We also have my code 2, which is has the, okay, so this is technically a tactic m, And it does not have a return value. No return value unit like void and C. Yeah, sure. And all that mycode2 does is it logs its argument. It says lean.loginfo calling mycode2 with a certain argument. Cool. Array is basically the same thing as list with different implementation. Mycode3, first thing it does is it says I'm calling mycode3, then it calls mycode2 on 7. Lean variables are immutable, but the do notation allows to break this using let mute. Okay, so let mute a array nat. Okay, so we initialize an empty array. This denotes it's an empty array. Yeah, sure. For I in standard array, I'm not sure I've seen this. I guess this is the loops through. Yeah, so this, I guess this syntax is just shorthand for 0, 1, 2, 3, 4. Okay, so for I in 0, 1, 2, 3, 4, we do, so we do mycode1, which is this function that 42 or square. We put that onto the array, and we log info about it, and then we run mycode2 15, and then we return the array. Okay, cool. So look at what, and now we look at what lean prints and see if you can understand where all the messages come from. So let me see if I can like trace through, right? Okay, so we run tac. Okay, let me see if I can do it without looking. So the first thing we do is we say we're running some tactic programs. Then we're going to let x equals mycode3. So we're going to say we're calling mycode3, and then we're going to do mycode2 7. So we'll be calling mycode2 7. So it's going to be calling mycode3, calling mycode2 7, and then we're calling mycode1 a bunch of times, which also logs it. So we're going to be like basically squaring and 42ing a bunch of things. So I will now look at it. Right, running got, what is this got? Oh, okay, so it also logs something with got, right? Okay, so we do 1, 2, okay, yeah, so that's basically fine. Okay, cool, we'll just do some run-in things. Okay, this is not exhaustive. Advanced topics include what is the theory behind monads, how to use custom monads, what are further programming focused functions and data structures like hashmap and foldm and IO, and throw error and panic, and partial functions for no termination checking. Great. What really is a proof state? On the core level, a proof is a term, a so-called proof term that testifies the truth of the given proposition. Yes. When we are proving a theorem, at every moment we have a partially built proof term with holes called metavariables. Most tactic steps fill one hole, formally assign one metavariable with a subterm, possibly containing further metavariables. Yes. Okay, the proof is finished once all metavariables are assigned, i.e. all holes are filled, i.e. all goals are closed. Metavariables are the variables with a question mark before their name. Okay, so like this, no, this maybe? So this is a metavariable, but this is not. I'm not exactly sure. Is this a variable with a question mark before its name? I'm not sure. Or is it just an underscore? I think this has to be a metavariable, right? Okay, as an example, we show proof if P implies P or P implies P and true, and write the partially filled proof term in between. Okay, so first thing we do, right, so we're here, we have P implies P and true. We intro H, so now we have P. And we went from P implies P and true to P implies P and true. We have a function that takes an H and has to return something, right? And so now when we do constructor, we have two goals, and correspondingly we have two metavariables. And the idea is that we're going to have our H, and then we're going to do and.intro, which is some function, and we're going to produce these two arguments to the and intro. The left-hand side we can find by assumption, and that's H, and the right-hand side is true.intro, which is just the trivial true. Wonderful. Okay, section 3. What are basic data structures around lean metaprogramming? Expressions, lean.expr, and QQ. Okay, this QQ will be good because I always want to understand more about QQ. Data in expressions, lean name, lean mvar ID, lean fvar ID. Okay. And printing string, format, and message data. Right. The data structure that is used to represent lean expressions is lean.expr. Due to the nature of dependent type theory, lean.expr is used to encode types, terms, and proofs. Right. Lean expressions. Right. So this is sort of different from like lean syntax, I think. right? This is like an actual Lean expression because the syntax gets like turned into an expression. Due to the nature-dependent type theory, it's used to encode types, terms, and proofs. Thus, lean.expr is also what is checked by the Lean kernel when checking proofs. Control-click on lean.expr to see its definition in the library. Check lean.expr. And the point is we see its definition, and this definition is that it's a type. No, we control-click. We have to like Lean expressions. Okay, this would work if I had it up in VS Code, but I don't know if it works because I have it in Lean. Like, can I do, go to definition, go to definition. Yeah, so I can open the docs here. I can see lean.expr, literal values for expr. So it can be a nat or a string, I guess. Okay, I don't, is it lean.literal or lean.expr? I'm a little confused. Lean.expr. Sorry, this is lean.expr. I don't know why I didn't get sent to this page, right? So, yeah, so, but I feel like this is what they always show in Lean metaprogramming tutorials is like the Lean expr. It can be a bvar, which is just a bound variable, a free variable, a meta variable. It can be like a sort, which is just like a type level. It can be a constant, which has been defined earlier. It can be a function application. It can be a lambda extraction. It can be a for all. It can be a let expression. It can be a literal. It can be metadata, right? Which I guess is hints to the pretty printer, store references to syntax notes, position information. This is, I'm a little, find it a little strange that this would be considered part of a Lean expression, but whatever. And then projection expressions. Used to create more compact terms, speed up reduction. Right, so A.1 is represented as the projection of the product onto 0A. Okay, cool. Right, this is the index of the projection. This is the struct. Okay, cool. Lean has a handy library, QQ, to help you build lean.expr terms with a convenient notation. Q ... is the type annotation of an expression, and Q, lowercase q, is an expression. It's a type annotation of an expression. See, I don't really get that, but if I mouse over, I might get something better. The type, yeah, so this is, I feel like this is a better explanation. Like Q of alpha is the type of Lean expressions having type alpha, right? So it's like, we have Lean expressions of type alpha, but I want to be able to refer, we have Lean terms of type alpha, and those terms are represented by expressions. And now I want to like be able to talk about the expressions in the same way. Like okay, I have some expression here, like, and I want to like pass it around. And so this is another prop. Great. Writing expressions directly is possible, but can take a bit of effort. Eval T1. I don't. These are both key prop. I'm not sure what this. Okay, no. This lets us see, right? So T1 is just the constant expression, which is true, and T2, right? So Q is a way of getting the Lean expression that gives you this. Right, so lowercase, I'm starting to see the value of lowercase q, because like the point is that we're saying that like, okay, we have for all p implied, and there's some Lean expression that gives you this. And the point is like, I would like to be able to write this really complicated expression, and the idea is I can just do lowercase q to get that. It's like, yes, it's a for all, and then the for all is applied to some universe level, and there's a bvar, which is the p, and the constant, yeah, like the p is here, and there should be like another bvar 1. I'm a little confused as to why we have bvar 0 here and bvar 1 here. Shouldn't it be the same bvar? Maybe it's a question of how, maybe it's that it's at a different index because we like introduced something that's a little confusing. Okay, whatever. type capital Q is not explicitly lean expr, but definitionally equal to it, and is not forced to have a correct type annotation. So you can think of QQ as Python type annotations. It can catch basic errors, but it is not forced at all. Lean expr equals T1, QNAT equals T1, and both of these type check. Cool. And T1E is a lean expr, and T1X is a QNAT. Yeah, so it's interesting. Clearly these types must be the same. Whatever. Another important type in metaprogramming is lean.name. And we've also opened the lean namespace. Wonderful. Nat.blah, an arbitrary name, and backtick T1E is the name here, right? So we now have the name for this expression. Sorry, this is a lean.expression, and T1E is also an expression. I'm not sure I really get the difference. Right, okay, I see. T1E is just this, and then the backtick T1E is a name. Okay, cool, sure. And if I print them out, it will tell me that there are certain particular names. Okay, cool. The way expr handles variables might seem messy at first. There are bound variables, named variables, meta variables, defined constant. Moreover, user-facing names of free variables and meta variables are not a unique identifier of a variable. Lean wants to allow multiple variables with the same name, so free variables are identified by fvar_id. Meta variables are identified by mvar_id. Right, the user-facing names are not a unique identifier. Okay, cool. These data types hide a name inside too, but that name, such as unique, should never be exposed to the user. Yeah, some like weird name. Okay. Showing/printing. Our basic printing function loginfo is a bit fancier than you might expect. I guess it should be what you might expect. Than what you might expect. In normal programming languages, we are used to a print function that takes a string. However, in Lean, loginfo takes a Lean message data. This means that it can show a term with mouse hover, showing types, control-click to go to definitions. Message data, interactive expression. Right, string, standard list of characters, format, string with information about how to line wrap nicely. Okay. A representation of a set of strings, right. A structured message data. Okay, interesting. Okay, cool. Examine the print of the following log info. Okay, so we're doing this run tag thing again. Log info, interactive message data T2 equals T2, string T2 equals T2, and format T2 equals repr T2. The function repr allows us to print the underlying data type. It returns a format. Okay. So these are the three things we've logged. T2 is this. We have this. The string, for some reason, does not have, okay, so if we do this, we're in this sort of mode where we can mouse over things and click on parts and see what's going on. Whereas with a string, it's just a raw string. And then a format is like so we've done some like fancy repr thing to see the underlying format information. But the point is that, we're basically seeing the entire underlying expression. Okay. I'm not exactly sure where the data about line wrapping is here, but whatever. Let us write the code for the 4 tactics used in this thing that we did. Okay, we have intro, constructor, assumption, and trivial. Great. So we're going to do those 4 tactics. This is section 4, basic API to modify the proof statement. A lot of the functions / types are hidden in namespaces. Lean, lean meta, lean elab tactic. So let's open them. Open lean, meta, elab tactic, and QQ. Cool. The easiest tactic to replace is trivial. Okay, so here is our trivial, right? This is run trivial 0, which is a tactic on unit. we retrieve the meta variable representing the current goal. So we do goal mvar_id get main goal, return the first goal. So this is a specific thing that we haven't seen before, right? We haven't seen. Yeah, this is the first time we've seen this particular tactic monad thing. And it lets us get the main goal, which in the case, like, so in the case where we're applying it, like the main goal is like true, right? And we assign it to be true intro, right? Okay, so we do goal assign q true intro. First attempt not ideal. Better to avoid low level mvar_id assign. We will see why. Okay, but the point is that like we get the main goal and we say the main goal is true, and this is the expression that we assign to it. Great. This is the q thing that constructs an expression to assign to the thing. We're doing meta_var_id mvar_id assign. Okay, that's fine. Goal and we see here that it works. We can run tac run trivial 0 and the goal is close. So run tac is just a way of turning a tactic M unit into like a tactic that we can do. Cool. That's like good to know, because there's a lot of stuff about turning a tactic into something that you can actually like write in a tactic mode proof, and I feel like this is maybe like a useful way of avoiding that. Okay. This works nicely, but the assignment is unsafe. It doesn't perform a type check. Let's try to close also the goal left p with run trivial 0 to see what happens. Example. So we're trying to prove this, and we say intro h constructor. So now we have to prove p and true, and now we've run trivial on p, which is wrong, and then we run trivial on this, and it's wrong, and it like gives us some error message. And I think the point is that it's not a good error message. Like mvar_id assign happily closed the goal. Then we correctly closed the goal. And at the very end, after the link kernel checked the entire proof term, we got a mysterious error that we cannot apply and intro p2 to true intro because it expects a proof of p and not a proof of true. Such errors are hard to decode, so it is better to ensure that we only assign a meta variable if the assignment has the correct type. Fortunately, Batteries has a function that checks if something can be assigned. Control to click on it to see the implementation. Okay. So wait, he's saying I can like command click on this and see the thing. So this is mvar assign if def eq. Assign if def eq. Meta m version of eval is act. Add to the variable assignment. This method wraps mvar assign, checking where mvar_id is already assigned and whether the expression has the right type. So it's basically just a safe way of closing that out. Okay, cool. So this is our version 1, and the version 1. So previously we had, how did we do this previous? So we're still getting the main goal, the meta variable representing the main goal, and this time instead of just assigning true intro to it, we are assign if def eking true intro to it, which is safer. And now we get an error in the correct place. Wonderful. However, the error message failed. Okay, wait, no. So apparently this is also not helpful. Why is this not helpful? However, the error message failed. It is not very helpful. To improve this, we can catch that error. Okay, let's see. Failed. The error message failed. Yes, it's not very helpful. Okay, it only says failed. The error message is literally the word failed. Okay. To improve this, we can catch that error and provide our own, more useful error. We can catch errors using a try-catch block, and we can throw errors using throw error. Okay, so here is our final take at run trivial, which I can tell because they don't have a number after it anymore. We get the goal. We try assign def eking it to true intro, and if we fail to do that, then we let the goal type equals goal type, and we say we throw it the error that we failed. The goal has the type this instead of true. And now when we do here, it'll say goal has type p instead of true. Wonderful. So the key thing to know there was like, okay, we have assign if def eq, and we do it inside this try catch block in order to get a sane error message. To implement assumption, we want to loop through all the assumptions and try to use them one by one. Okay, yeah, so we had 4 things, and they were, what were they again? Assumption, trivial, constructor, and intro. So we did trivial, and now I guess we're doing assumption. To implement assumption, we want to loop through all the assumptions and try to use them one by one. The list of assumptions, which appears above the turnstile in the info view, is called the local context. How do we get the local context? In general, each meta variable, i.e. goal, has its own local context, but we can just use with main context. With main context. Use the main goal local context. Okay, sure. Each meta variable has its own local context, but we can use with main context. This puts the local context of the current goal into the monadic context. And then we can retrieve the context using get LCTX. Okay. So first we can just print the assumption. Okay, so example. True. Run tech. Here's what we're doing. We're with with main context do. Okay, so this is some weird thing. This is something that like takes a tactic, and the point is that it's a tactic M to a tactic M, and it's basically running the same tactic but with the main goal local context, I guess. I don't know if I'm totally clear on why it's necessary. Like, why isn't the main goal context just the thing that automatically exists for the tactic to run on? But whatever. So with main context, do let context equals get LCTX. What is this again? Get local context. The list of assumptions is called the local context. So this is, I guess, this is like this is the list. It's not a list, but it contains all of the data about the different assumptions. Go through all local declarations for decal in local decal in context. Do log info and the inspection. So let's see what it logs, right? So it logs example. Okay, so it logs nat. It logs n and hn, which makes sense. It also logs like the goal as a whole, which I don't really get. Is there a way to just get the local context, which is just the values? We have all the components. So let's implement the assumption tactic. Run assumption. We don't have to start with do here, but we can. But we do have to do it. Okay, so like let's just like check, right? We can do a do here. We can if we want to, but we do have to have a do here. So if we delete this, it'll shit the bed. Okay. We have all the components. Let's implement the assumption tactic. Run assumption is a tactic M unit. We do with main context. We get the goal. We get the local context. For each declaration in the local context, we do the following. If decal.kind is not equal to .default, then continue. Okay, so this is just something where like, okay, we're getting rid of some cruft. Maybe this is the thing about not getting the not getting like the initial context up here, like this thing. Is that what that's excluding, perhaps? Yeah, so these are defaults, and this is not a default. Okay. If decal.kind is not equal to default, then continue. Then we do another try catch pattern, right? So we do try to assign if defiq okay, so we have our decal, and we're going to do the decal.get the variable ID for this decal, and we're going to fvar constructor that. So we basically are going to turn that into an expression. Okay, so this gets us our expression, and the expression that we wanted is the expression that contains just the particular thing that we might be applying to solve the goal. And then if we succeeded, we are done. And then if we catch, then we ignore the exception. Right, so we're basically trying a whole bunch of things. All of them will fail except maybe one. And then at the very end, if we failed, we say assumption not found. Okay, cool. So just to check that it works, we can do that. We can do a run trivial. And the whole point, okay, so let's try and like, let me see if I can, right. return. So here. Okay, like, what happens if I like put this here just to like see what's going on? I can do this, and now it will tell me, presumably, like, in line 373 that it found this thing, and it also found P, this prop, and H, which is this P. Yeah, that makes sense. Great. And presumably, if I put it here, it will no longer tell me that it got this weird thing about, sorry, then continue. If I put it here, then when I mouse over, there's no more of this like whole context, like the entire list of everything. So I'm not exactly sure why that's why that was there to begin with, but okay. But the thing is that it works. The remaining two tactics. Okay, so we did trivial, we did assumption. Now we're probably going to do constructor. The remaining two tactics require creating a new meta variable. Yes, right, because with constructor we have a meta variable that we need to fill in. And we're doing like an and intro or something. And we need to create more meta variables. We need to go from one meta variable to two meta variables. Okay. A new meta variable is created using make_fresh_expr mvar. However, a good practice is to make the goal variable synthetic opaque. Then Lean knows that they are somewhat important and doesn't assign them willy-nilly. One way is to use the following function. Make fresh expr synthetic opaque mvar. Although if you control click on it, you'll find that it just calls make fresh expr mvar with a specific kind. Okay, cool. Now let us define run constructor. Right, so we're doing run constructor now, great. In which we will decompose and. We will not attempt general constructor. Okay, so we're just doing and. That's cool. First, we just write the function that reads the type A and B from the goal and extracts the two type expressions A and B. So extract and goals is a tactic m expr. Okay, so it's a tactic monad that returns two exprs, namely the expressions for A and B. So we call get main target, which returns the expected type for the main goal. Cool. Add a Q annotation to target. Must use have, not let. Okay, so quoted target, Q prop is the target, yes. So it's a Q prop. It was an expr, but now it's a Q prop. Great, because these are typed like it said before that Q of A is like definitionally equivalent to like the type of expressions, but this is just something to like ensure that it is an expression specifically of type prop, which it should be. Now we match quoted target with. Okay, so this is a QQ match. So this is like, I think the tilde Q is what's special and new here. So this is QQ match. Must run in meta m or higher. Okay. QQ's expression, matching in meta m up to reducible def equality. Okay, with a match expression. So the point is we have our quoted target and we are trying to match it to an and thing. And we have some $ as well. Wow, this is crazy. Yeah, but it's like, yeah, and I mean, I guess it's totally analogous to what we have in here. So like if we had nat.gcd, it would be this. If we had this, it would be handle add. Great. Goal target is not of the form this, right? So if it's not of this form, we throw an error. Great. So that's extract and goals. Cool. QQ is, okay, so now here's the second version of that. Same thing. QQ is handy, but it is worth knowing how to do these things quote unquote manually. So let target get main target, an alternative syntax to this match with thing. We say let and equals get, right? So this is like a pattern match, I guess. We're saying that it's something that's constructed out of an and these two things. Get app function args. Return the function and arguments of an application. Right, okay, great. And then we return P, Q. Cool. we throw error if it's not of that form. Let throw error. This is interesting. I don't think I've seen this before either. This is some syntax for, like, we get app function args. I guess this is a, if this fails, we go to the throwing in the error. I don't think I've seen like this syntax before. Note that the non-QQ version requires the term to be more exactly matching. Before matching, you might want to call the following two functions: instantiate mvars and whnf, reduced to weak head normal form. Okay. Exceeds the scope of this tutorial. Okay. Let's check that our decomposition of and works. Example. So we have PQ props, we have H as P and Q, and we have the goal P and Q. Run tac. We extract the end goals 1, and we see that we get QQ extraction gives P and Q, and the expert extraction gives P and Q. So they both give P and Q. Cool. Replaces the main goal. Okay, cool. So run constructor. What are we doing now? So now let's go ahead and make constructor, right? So how does constructor work? We are going to replace the goal with 2 separate goals, right? And how we do that? Okay, so again, we have this with main context do. Try to comment out this line to see what breaks. Okay, cool. Right. Hilarious. The assumption line breaks, not the other line. Because I guess the point is that, so maybe we'll explain that in a moment. With main context do, like, hopefully this will answer my earlier question about why we need this with main context. But with the main context, we get the goal out of the main goal, we extract the and goals, and we say that they're both props, cool. And then we say we do this make fresh synthetic opaque thing to get a new A, and we make fresh synthetic B to get this. And then we goal assign those 2 things, right? So this is basically just saying, okay, once we have those, we'll just assign them. And then we replace main goal with 2 additional goals. So this is something that like lets me make more goals in the info view. Cool. We can be brave here with assign. Can we be brave here with assign? So the question that's being, okay, so many questions. we instantly got like asked like a bunch of questions, I feel. Okay. So the reason we can't do this is that if we're not doing with main context, then we do this intro, we run constructor, and now the assumption is not found. What I don't really get is why the assumption is not found. Because it looks like run constructor succeeded. In that it's split up into 2 things. Now, P and true, right? So in both cases we have P. Is the, what could possibly be going on here? With main context do. I feel like I don't have enough of an idea of like how, like, am I supposed to get this? This puts the local context of the current goal into the monadic context. Okay, but like whatever run constructor is implemented as, run assumption is defined to use this with main context thing. So I don't get why there would be a problem with run assumption. Is the point that like after this tactic was done, like, is the point that like after this tactic is done, because we didn't say it was in the main context, we just like go back to the beginning? Here, let me go to the assumption, and can I like change this? Can I throw error instead of this? Can I throw error like m exclam assumption like I want to get the goal, assumption goal not found. Okay, so that is there now. And if I go down here, not found. What the heck? Okay, assumption, and then it has this whole thing, not found. Right. So the point is that the reason assumption failed, is it going to be prettier if I assumption goal? How do I print out again the not the like, not all the fancy stuff, but just the like string version of it? S. So S, if I do S exclam, right, so this is something I added. This is what I added. And if I do S exclam, this is failed to synthesize string var ID. Okay, so that doesn't work apparently. Whatever. M. And this doesn't work because it's saying that the assumption we were looking for, right, for whatever reason, it wasn't like, it was thinking that we had to not just look for P, it was thinking that we had to look for this entire thing, that we had to look for P implies P, which I'm not really sure I get why that would happen. There's no explanation of why that would happen. That's frustrating. Okay. Maybe there's an explanation down here. Alright, like if I comment this line again, it works fine. Yeah, I really don't get it. Okay, whatever. And so the other question is, can we be brave here with dot assign, as opposed to the other instruction that we were given to use, which is assign if def eq. I think the point is that, right. So I think the point is that, like, technically, yes, there's no way that this can go wrong, because here we have extracted and goals, and if it wasn't a proper and goal, this would have failed. And so we know that it's an and goal, and so we're assigning something that we know it will work because we know it's going to be an intro of this left and right thing. So I think it is, the idea is that we can technically be brave. And then we replace the main goal. Okay, cool. Well, yeah, no idea why it causes that to happen. The implementation of intro has the most hidden intricacies. Do not worry too much if you do not fully understand. Okay. There's no way you are going to understand this. Okay, run intro. Right, the point is, to implement intro, we have to like do something that will get a particular, that will like peel off from the context, this for all thing, right? So we get the main goal with main context do, as always. We get the goal, we get the local context. we let for all e. So we say, right, so this is this match statement. Like, I'm beginning to just sort of get an intuitive sense of what this is. The point is that we match to this goal get type. We say that the type of the goal has to be a for all if we're going to imply the intro tactic. And if it's not, we say the goal is not of the right form. Then we allocate a new, fresh, free variable, and we put into a new context. We put the variable that we just made into a new context. This is this variable. Convert bvar to fvar. Okay, sure. And at some point, the point is that we have to like create the proof, and then we have to apply the proof. Right, so let body.instantiate do goal.assign new val. New val being, yeah, so we're going to make a lambda, we're going to like make a lambda application, right? Make a lambda thing where we, yeah, so the value that we're giving to the goal now is this lambda type, and we're assigning that to the goal, and then all we have to do is replace the new goal with this like new mvar, which is here, which is this synthetic mvar, which is the body that has the new thing in the context. Okay, sure. Since Lean already implemented intro, there's a shortcut. Okay, interesting. We can technically just do goal.intro name. Let goal get main goal, and we could say it like goal.intro some name, and we can replace the main goal. Okay, interesting. And now we can do this. And now we have to give a literal name. Interesting. Okay, in this example we did goal-oriented tactics. So let us show how we could add a new have element to the local context, a custom have. So let us show how we could add a new have element. So okay, I guess the point is that okay, we did these 4 tactics, and now we're going to implement have as well. Okay, cool. We want to emulate have hb equals hba. Right. Have hb run tactic. Okay, so with main context do, we're going to get the goal, which is b, and we're going to get the local context. Find appropriate free variables. I'm a little confused because it's like have takes like a name as an argument in some ways, right? So find appropriate free variables. Some ehab. Find from username hab. Okay, so we found hab. We found ha. And when we construct the apply expression, e, t is the infer type, t equals b, e equals hab, hb. Goal is context implies main goal. Like goal 2, goal is, okay, yeah. So the point is, when you do a have statement, you have to make 2 new goals. The first goal is whatever you have to like construct something of type A. Yeah. And the second goal is you have to construct something. You have to like from that. So goal, yeah, so we're using this intro again. So we're like introing the HB that we made. And now we have to use that to replace goal 3. This is a little weird. We're replacing main goal with goal 3. I guess the point is that like this is like a simpler version of have where we have to like automatically apply the things that we have. Yeah, okay, sure. It's like it's for like exactly this structure, this like application of 2 things structure. It has to be that way. How to declare syntax for a new tactic. Like, isn't there this? Yeah, this thing is like named maybe like replace or something. How to declare or specialize. I guess specialize like replaces the name, so it's not exactly have, but sure. Section 5, how to declare syntax for a new tactic. Right, okay, so this is the section I'm less interested in. especially because we've like been shown a cool way, which is to use this run tag thing. How to declare syntax for a new tactic. We have discussed how tactics work internally, but another important part of tactics is the syntax we use to call them. In dealing with syntax, we use the types lean.syntax and lean.tsyntax. Don't worry about the implementation of lean syntax, as it is quite messy. Check lean syntax. Check lean tsyntax. Right, so yes, the type of syntax trees. Cool. Just like Q is an annotation version of expert, tsnet is an annotation version of syntax. However, syntax annotations are just a name. The most common ones are term, tactic, number literal, identifier literal, command, top level command, like def or eval, do lm, do notation. Cool. You can construct syntax using quotations like kind, middle bar, syntax. Okay. This only works in a monad similar to meta-m, core m to be precise. Okay. So S1 meta-m, tactic, apply, and intro. So we can get these like terms. We have these like S1, so now I can just eval S2 and it will, okay, no, this is not what I expected. This is just some like big syntax expression. Is the point that this is telling me like what line, what like point in the file it is, maybe? Okay. Now that we can construct syntax, we can make a macro. A macro is a rule that operates on syntax, and these rules are used when the syntax is being elaborated. My constructor syntax, tactic, apply, and intro. Right, okay, my constructor, my trivial. So we're doing all of this, all the like my's now. Right, so now we can say intro age, my constructor, my assumption, my trivial. Cool. We show to assign the monadic programs to the appropriate syntax using the elab command. And the point is probably that we could like do the exact same thing. Wait. No, that we've actually gotten a different tactic here. Never mind. This is like, we're like, this is apply and intro and tactic exact true intro. So these are like these are just tactics that are very specific to this example problem we keep seeing. For intro and assumption, we show how to assign the monadic programs to the appropriate syntax using a lab command. Beware that syntax defining syntax is quite sensitive to whitespace characters. The following example, you cannot put a space between a and colon, right? Also, the tactic notation as shown earlier is best kept without spaces. A has type this, okay. A ident tactic, right, as assumption, my assumption tactic to run assumption. So we can make like a echo tactic and a square nat tactic, fun. Right, so we can do these, right? Echo hello world says hello world, square nat 5 gives 25, square float gives this, my check gives this. Not implemented. Left as exercise. Right, cool. The macro and a lab commands are nice, but for more complicated syntax, you may need a bit more flexibility. Achieved by first defining syntax with a syntax command, then defining the meaning of that syntax with a macro rules or a lab rules command. For example, the above tactics can be defined as follows. My constructor. Right. Yes, macro rules like this. Okay. We use $thing anti-quotation. Matches optional syntax. Let's test it. Okay, so this is how we can write a list of things to apply. Simp only. My simp rewrite is simp only. So this, okay, so we have like a list here. Let's try and understand this. To match optional syntax or a list of syntax, we use the $, open square bracket, close square bracket, anti-quotation. We have that $, open square bracket, close square bracket, question mark matches optional syntax, and $, open square bracket, close square bracket, comma, asterisk matches a possibly empty comma separated list of syntax. Square brackets without a dollar represent a explicit open square bracket and close square bracket. Yes, right, okay. without a dollar are explicit open square bracket and close square bracket symbols in the syntax. Not all syntax kind annotations are required here. They have been added for clarity. Okay, so my simp rewrite is something, okay, right. So it first uses an $signed open square bracket. So we have to say my simp rewrite, then we have to put an open bracket, and then we have a term, and then we have a possibly empty comma separated list of terms. We have at least one term, and then I guess we have a comma, and then we have a list of additional terms, and then we have a close square bracket, and then we have the optionally a location, which is this at thing. So we can do my simp rewrite, and we can do it with like at as well. Okay, cool. And just to like explain how it gets turned into something, right? So my simp rewrite, we have ES, which is the remaining E and ES are the tactics to are the rewrite rules to apply. So the thing we do is we do simp only. So in order to do this, right, we first do it simp only with the first E, and then we do my simp rewrite with the remainder of the E's, I guess. So this is like a weird like list induction, recursive definition. Cool. Or we can use the lab rules to loop through the array of terms directly. Cool. Syntax matching can get quite complicated. Unfortunately, there's no universal guide on these intricacies. Some advanced things you could do. You could define syntax. You could have defined with the backwards arrow. Right. A syntax category. Terms in natural language, right? So I can do syntax category plus syntax category. So I can do macro rules, and now I can like write 1 + 2 × 4. Cool, interesting. Much more to say. You can check out the more advanced metaprogramming book. Yeah, so I've gone through this before, and this was like maybe a condensed version of this metaprogramming book, I would say. Yes, problem stuck on these bugs. There's like a gotchas page, interesting. And there's like its own, the quote library has its own thing. Oh, all right. Very fun. Okay, cool. So we got through all 762 lines of this. I think that's probably good enough for today.